Hello, everyone, and welcome to this webinar on ammonia as a fuel, where we'll discuss material integrity challenges in the next generation energy system. This webinar is co-organized by the EU-funded projects Single, FUELSOME, and AMON. And we have the pleasure to have 6 speakers today. We've divided the webinar into 2 sessions with a short break in between to allow you to stretch your legs and get some coffee before we move on to the next one. As Giacomo already said, there will be time for questions after each of the presentations. And then we're planning to have a 10-minute Q&A comment session with all of the presenters at the end of the webinar. So we hope to keep you with us towards the end and look forward to some interesting presentations. To kick it off, we have Santeri Saxlin from VTT, who's going to give us an introduction to the topic.
All right, do you see my screen? I hope you do.
Yes, we can see.
Okay, yes, thank you. So warm welcome from also my side. My name is Santeri Saxlin. I work in the VTT, so the Technical Research Station of Finland. I will give the first presentation of this workshop. This is going to be a kind of warm-up for the topic. So introduction to ammonia use as a fuel and the main challenges. So the content of my presentation will be as follows. A few words about the VTT, then the introduction to ammonia fuel use, then some ammonia related issues, and then introduction to the FUELSOME project, which was the kind of trigger to have this workshop from the ammonia topic. So VTT is basically one of the leading research organizations in Europe. We basically work in the field between the universities and the industry, where we collaborate both with them by using the basic level research from the universities, and we turn them into the projects and demonstrations with the private sector. For example, making a synthetic diesel from green hydrogen from the electrolysis and direct air carbon capture. The team where I'm coming from is the hydrogen production team. So we basically focus on the electrolysis with all the technologies, solid oxide, PEM, alkaline, and anion exchange membranes. We have around 25 years of active experience with these technologies, and our tasks vary quite a lot from experimental research to modeling, and we are really reliable partner in this kind of activities due to our long experience. Okay, so what is ammonia? Basically, the ammonia, when it's used as a fuel, it's a hydrogen carrier. The molecule itself contains 3 atoms of hydrogen and doesn't include any carbon. So this means that when the ammonia is combusted or oxidized, it doesn't produce any carbon dioxide emissions, which is basically the biggest motivation behind all of this idea of using ammonia as a fuel. But however, this requires the green hydrogen production, so we also need to handle that. Ammonia can basically be used 2 different ways. You can use ammonia directly, for example, with the solid oxide fuel cell, where the ammonia is then used to create the electricity or create the power to some device you're using or application. Or you can crack the ammonia to hydrogen and nitrogen and then use that fuel feed in the solid oxide fuel cell or combustion engine. At least or that would be probably the most practical way to crack the ammonia in degree that it's manageable to use in the devices. But from this topic, we will hear more in the later presentations. Other motivation behind the ammonia, it's the energy density it has. It has quite high volumetric energy density. For example, if you compare it to the hydrogen, it's even a bit better than the liquidized hydrogen because it has considerably low point where it liquidizes. So already at 8.6 bars in the room temperature, you can have liquid ammonia. So it's easily stored in the containers or gas bottles. It's also quite widely used in the industry, for example, in the fertilizers and chemical industry. So it's not that new substance to be used. So we kind of have also already ways to deal with this ammonia. But then the issues with the ammonia, basically, when we are using the ammonia at the high temperature, it creates like a harsh environment for the metal components. For example, the picture on the right, you can see metal alloy 253Ma, which is used in the high temperature BOP components, balance of plant components, such as heat exchangers. And this particular picture is from the sample that has been under 5% ammonia with the nitrogen and hydrogen over 334 hours and 750 degrees. And you can see it's already damaged quite a lot. So basically, the ammonia has nitrated the whole sample into ceramics. So we need to find a way to handle the ammonia in the high temperatures. Other issue is the safety. So ammonia is extremely hazardous substance. It's causing damage to the cells and tissues. Already at 30 ppm level of concentration, it's considered harmful if you are exposed over longer time, and 5,000 ppm when it's inhaled, it can already cause death. So it needs to be handled carefully if you want to use it safely. Then the introduction to FUELSOME project, which was the trigger for having this workshop from our side. So in this project, the aim is to develop a solid oxide fuel cell technology for long distance shipping applications that can be run with ammonia and methanol. The project was started in 2002. It has 2.5 million euros of EU budget, and it's a 4-year project. So at the moment we are in the last year of the project. And in the consortium, we have eight partners. To give you an idea what we are actually doing in the project, I'm going to go through the objectives and give details on whose responsibility is each objective. So the first one is to design and model a complete technology concept for product to end use, taking into account the fuel quality and storage and distribution requirements for this technology concept. This is the responsibility of AEE and Warsaw University of Technology. Then the objective 2 is to take this idea into the lab scale testing. So we are testing with Elcogen the stack modules and materials with the ammonia and methanol-based fuel feeds. And we also developed this fuel processing unit that can be used with both fuels. Then the objective 3 is done by AVL, who designed and built the test station for the system scale testing with both of the fuels, where they will see the system level phenomena like overall efficiency and so on. Then the objective 4 is done by University of Applied Science in Zurich and Athena, where they take this technology concept in the under techno-economic assessment and life cycle assessment. And the objective 5 is the dissemination, communication, and exploitation, which is done by EBOS. So basically, this kind of activities that we are having at the moment. That was all from my side. I hope you enjoyed and got the warm up for the topic. If you have any questions to me, feel free to ask. I will stop sharing.
There is actually
I guess
a question in the box from Logi. I hope it's pronounced correctly. Sorry. So, do you expect long-term issues with metal nitration of components in energy converters, such as SO, FC, and combustion engines?
Yeah, I think it depends. I think to this question we will hear more from the other presentation, but I think we will have like strategies to mitigate the nitration. But yeah, with the commonly used metals, it is an issue, but I think we can find a way to deal with it. Probably Alpha Level and others will give answers to this one.
Okay, thank you. Any other question? You can open your microphone and ask directly.
Yeah, I think it's also nice to hear the voice.
Yes.
If possible.
Of course, I recall you that we will have also at the end, you will have time to make question at the end of this webinar. So I do not see any other question. So we pass to the next speaker, Belma Talic. So Belma, you should be able now to share your screen. We can see you. Thank you.
So hello again, everyone. My name is Belma Talic. I'm a senior research scientist at the SINTEF, independent research institution in Norway. And I will present results from the single project on degradation resistance of alloys for the balance of plant of an ammonia cracker system. So as already mentioned, this work is a part of an EU and Clean Hydrogen Partnership funded project, SINGLE, which is working to develop an electrified single-stage ammonia cracker to produce compressed hydrogen. The project is coordinated by Corstec Membrane Sciences and includes 7 partners from Spain, Italy, Slovenia, and Norway. We started the project back in May 2023 with a duration of 3 years, meaning that we're now approaching the final 6 months of the work. The overall aim of the single project is to develop and demonstrate an ammonia cracker module that's able to produce 10 kilograms of hydrogen per day. The system itself is based on a so-called proton conducting ceramic electrochemical reactor, which integrates the processes of ammonia cracking inside with hydrogen-nitrogen separation across the membrane and electrochemical compression of hydrogen into one single-stage process. This process intensification allows for tight coupling between, on one hand, endothermic ammonia decomposition reaction, with, on the other side, the exothermic processes of hydrogen separation and compression, which enables us to potentially increase the overall energy efficiency of the cracking. The reactor itself and the module will be operated at temperatures up to 750 degrees centigrade, aiming to deliver hydrogen up to 30 bars. Because of this proton conducting membrane, the proton conductivity of the membrane relies on humidified feeds. The system will be exposed to wet ammonia containing gas mixtures. So in addition to the proton's ceramic membrane, which is really the core technology, our ammonia cracker system will also include several so-called balance of plant components. So these are typically heat exchangers, pumps, valves, piping, and so on, which all will be exposed to wet pressurized ammonia at high temperature. There's a lot of knowledge out there available on the nitridation resistance of alloys from, for example, ammonia synthesis and nitriding of steels. But most of this knowledge is based on dry conditions and also at slightly lower temperatures than the maximum operating temperature that we are aiming for in SINGLE. So one of the key tasks of the SINGLE project was to identify alloys which were able to tolerate the specific operating conditions that we have so that we can operate it safely. For the experimental test campaign that we have done in the project, we have included 7 different alloys that you see listed here. These include nickel-based alloys in Inconel types. We have some austenitic stainless steels, a ferritic stainless steel, and an alumina-forming ferritic steel. In this plot, you can see the main alloying elements, so nickel, iron, and chromium content in the different alloys. And as you can see from the plot, we try to cover in this test campaign a range of different compositions spanning from high nickel and low iron content on the top here to low or no nickel content and high iron content in the bottom. To study the nitridation resistance of these alloys, we have at SINTEF established a dedicated ammonia corrosion rig that allows us to carry out exposures to ammonia containing gas mixtures at up to 20 bars of total pressure and temperatures up to 900 degrees centigrade. And the rig itself consists of an alloy-based reactor with swage law components, as you can see picture inside the furnace here. And we have a needle valve at the outlet, picture here, where we have pressure control. The system is made with an in-house gas mixer where we can send in nitrogen and hydrogen gases and mix them with liquid ammonia and liquid water, heat everything up to evaporate the liquids and mix them together before sending it into the reactor. And the rig itself is located into a dedicated ammonia lab where we have high ventilation capacity, several ammonia sensors, and other necessary safety features to operate safely. So the different candidates alloys that were studied were all acquired in sheet form and cut into coupons that you can see pictured here. They were mounted inside of the reactor using silver wire. For the testing, we had at least 3 different coupons of each alloy type that were arranged vertically within the reactor in order to account for any variations with respect to position. We carried out the exposures at 7 different conditions as presented in this table. The temperature was varied from 550 to 750 degrees centigrade. We varied the ammonia concentration from 6 to 23 and 85%, with the remaining gas being nitrogen and hydrogen in a mixture equivalent as cracked ammonia. And finally, we evaluated the impact of steam. Most of the test was done with 2% of steam in the atmosphere, but we also did test at 650 and 750 without any steam present. All of these 7 exposures were done at 20 bars of total pressure for 200 hours of duration. And we did heating and cooling in dry nitrogen atmosphere. To evaluate the nitridation resistance, we recorded the weight of the alloy before and after exposure to ammonia. And generally, we saw that the mass gain corresponded quite well with the extent of nitridation. So the graph here shows the mass gain as a function of ammonia concentration measured at 550 degrees centigrade. For most of the alloys, we found that increasing ammonia concentration also increases the mass gain, so it leads to more severe nitridation. In this plot, the alloys are arranged from low to high iron content in the alloy. And we can also see from this graph that as we are increasing the iron content of the alloy, we also increase the nitridation. And for all of the alloys, except for 625 in Cornell, which was fairly unaffected by all of the test conditions, we see that increasing ammonia concentration greatly increases the nitridation. And for these ferritic steels, 444 and EF101, we observed that at the highest ammonia concentration, the alloy coupon was completely disintegrated after the 200 hours of exposure. This is why we don't have any points here at the highest concentrations. We also looked at the cross sections of the alloy coupons after the exposure, here illustrated for alloy 800 HT. Where we also can see that at 550 degrees, increasing ammonia from 6 to 23 to 85%, both the depth of nitridation increases, but also the amount of nitrogen dissolved in the nitrated area. So in the SEM images, you can very clearly see a contrast difference from the near surface area, which is darker, to the base alloy. So this darker area is where we, by EDS, also detect nitrogen dissolved in the alloy. For 800 HT, we can see that at the highest concentration of ammonia, the nitrated zone has extended almost 200 micrometers beneath the surface of the component. And we also have started to have phase separation in the nitrated area if we zoom into this the lower part here. And we also see intergranule cracking of the nitrated zone. The next graph here shows the impact of temperature, which was studied at 6% ammonia and wet conditions. In this case, we see that alloy 600, 800 HT, and 316L all have an increasing mass gain with increasing temperature, meaning they become more nitrided. While the ferritic stainless steel 444 actually shows the opposite trend. Here we see that as we go from 550 to 750, the mass gain decreases. The alloy 625 and 310S had the peak at 650 degrees centigrade, but again, 625 was quite low on mass gain at all conditions. And finally, the alumina forming EF101 was quite invariant with temperature. The differences in the temperature dependence of the different alloys can, to a large degree, be understood if we inspect the sample cross-sections in DSEM. Here we see alloys, the ferritic stainless steel 444 and the nickel-based alloy 600, plotted or shown at 6% ammonia, 550, 650, and 750 degrees centigrade. For 444, we see that at 550 degrees, there's an even layer that has become nitrated. We have some cracking starting to occur in the nitrated zone. When we increase the temperature, we see an increased depth of nitridation, but the content of nitrogen in the alloy has been slightly decreased, and we don't see any cracking anymore. And then when we move to 750 degrees, for this alloy, we don't see any nitrogen anymore. Instead, we see that a surface scale has formed on the top of the alloy. With EDS and XRD, we could see that the scale was composed of silica closest to the alloy, followed by chromia and manganese chromium spinel. So as already mentioned, these tests were done with humidified conditions, 2% of steam. And it is clear that the added steam was sufficiently high in oxygen partial pressure to oxidize this alloy, and that the oxide layer that was formed probably acted as a barrier against nitridation. In contrast, if we look at the nickel-based alloy 600, we see, as we saw from the mass gain, that with increasing temperature, the depth of nitridation is increased. Also for this alloy, we see oxidation at especially the higher temperatures. But in this case, the oxidation is intergranular and internal rather than forming a continuous surface layer, making it non-protective. The final results that I will show are on the impact of steam, which we compared at 650 and 750 degrees centigrade, in both cases with 6% of ammonia. Also in this case, we see that the impact of steam depends on the type of alloy. For most of them, we see that there's the same tendency at 650 and 750, so I'll remove the 750 to add some key points here. For alloys 625, 600, 800 HT, and 316L, we see that the mass gain is lower in dry conditions, while for the ferritic steels 444 and EF101, we see that the mass gain is lower in wet conditions. So I said that for most of the alloys, this was the same at the two temperatures. The only exception is the 310S, which had at 650 shown here, lowest mass gain in dry conditions, while at 750 we had the lowest mass gain at the wet conditions. Again, we look to the SEM to gain better understanding of what is going on. And again, I have used the alloys 444 and 600 as an example. For 444, we already saw that we, in wet conditions at 750, were able to mitigate nitridation by forming a continuous oxide scale on the surface. When we switch to dry conditions, the partial pressure of oxygen is insufficient to cause any oxidation of the alloy. So instead, then we are allowing nitrogen to go into the alloy and react, forming chromium nitrides. For alloy 600, we see that the extent of nitridation is, as we saw from the mass gain, lower in dry conditions than in wet conditions. To understand this, we measured the degree of ammonia decomposition at the outlet of the test reactor using FTER gas analysis. What we saw from this was that at 750 degrees and wet conditions, more of the ammonia was retained at the outlet compared to dry conditions. So to say differently, we had more cracking of ammonia inside the reactor in dry conditions than in wet. So in practice, the alloys were exposed to a higher concentration of ammonia in wet conditions than in dry conditions. And this is why we probably see a higher degree of nitridation of wet. So I finally reached the conclusion. In summary, what we saw from this study, studying 7 different alloys and 7 different exposure conditions that generally the nitridation resistant increases with decreasing iron content and increasing nickel content of the alloy. We saw that the ammonia concentration had a very large impact on the nitridation potential, and it led to increased degradation of most of the alloys. We also saw that increasing temperature and wet ammonia increased nitridation of many alloys, but for some, such as the Freitag stainless steel 444, it can actually mitigate nitridation because it promotes formation of an oxide scale. Steam had an impact on both oxide scale formation and the ammonia decomposition. So depending on the type of alloy, it can both decrease and increase nitridation of the alloy. And finally, we concluded that alloy 625 was the alloy that we tested that had the best resistance when we considered all of the different testing conditions. So with that, I would like to thank you all for the attention and welcome any questions.
A couple of questions for you. The first one, maybe you already answered, I don't know. How much H2O is present in the process? This is by Rob. And the second one, I may have missed this, Yusman said, but what's the exposure time for these alloys in NH3 at high temperature?
Yeah, so the content of steam, when we added it intentionally, was 2 volume% in all cases. In the dry conditions, we did not have any intentional additions of steam. The duration of all of the tests were 200 hours in total.
Okay, thank you. Again, any other direct question? Please open your microphone. And we have a hand raised, please.
Yes, hi. I hope you can hear me. Here's Jayum from Deshema.
Yes.
I have 2 questions, actually. Thank you, Belma, first of all, for the great talk. The first one is the addition of additional steam. I completely understand. So you increase the oxygen partial pressure. So we have an oxide scale, which is a barrier against nitridation. But steam is well known to induce chromium evaporation also. So how does that correlate to your mass gain data? So we are, on the one hand, mitigating nitridation, but also we are evaporating chromium out of the alloy. The second is actually a funny question. So I saw that you're using 316L tubes. So do you inspect any damage on the tubes, or how often do you need to change them? Thank you.
Yeah, thanks a lot for those questions. Regarding the chromium evaporation, I don't believe that it's impacting our mass gain results that much. We should remember that although we're adding 2% of steam, the atmosphere otherwise is quite reducing because we have such a high concentration of ammonia. And in order to have significant evaporation of chromium, we would need to have a higher partial pressure of oxygen as well, I would think. I haven't seen any measurements of evaporation in these conditions, but at least in hydrogen mixtures, the evaporation of chromium is greatly reduced compared to oxidizing wet conditions. But it would be, of course, we cannot rule out that it's not influencing it to a small degree. But what we can say that is when we compare our SEM analysis, so looking at the depth of nitridation and the amount of nitrogen dissolved in the alloy, and compare that to the mass gain data, there's a very good correlation between the two. So most of the majority of the mass gain that we are measuring is because of nitrogen going into the alloys. For the second question regarding the test setup, I think that's also, it's something that we spent a long time evaluating and that we are continuously evaluating. So I can maybe add that for this steel-based reactor, which is in the hot zone of the furnace, we initially used alloy 800 HT, but we have now switched after seeing the initial results from the testing here in Single. We have switched this to alloy 625 because that was more nitridation resistant. For the gas tubing, the heated zone here is made of Inconel 600, and then the cold zone is made of 316 components. And also these Swagelok components are 316. So we've checked with laser thermometers and so on to ensure that the temperature of these Swagelok components are sufficiently low where we don't have significant nitridation of the components. But it is something that we are paying close attention to, and we are occasionally taking out parts of the rig and inspecting them and trying to get an understanding for when we have to replace the different components in order to operate safely. So I hope that answered your question.
We actually have a couple more questions in the box. I think we have some minutes to answer. The first one from Petar. Do you think that the tendency for high water content up to 35 volume percentage would be the same for the different materials as was in the represented test? And then I will go with the other one, if it's okay for you, Belma. From Jorg, the reactor is vertical downflow. How is it ensured that the lower material probes are exposed at the same ammonia partial pressure compared to the upper probes, meaning that the lower probes have the same amount of fresh ammonia? Thank you.
Yep. I can maybe take the last question first, since I'm on this slide. So you see here from the illustration that our samples are arranged vertically downwards in the reactor, and of course we have ammonia fed from the top entering to the bottom. So we do expect, since the reactor itself is made of alloy, we also have alloy samples on the way down here, that there is cracking of ammonia taking place. We also measure that by FDR at outlet, so that there is probably a concentration gradient going from the top to the bottom. We have, as I mentioned here, we have 3 samples of each type that we arrange on top of each other. And generally, we haven't, under, I would say, most of the conditions, we haven't really seen any systematic variation in the mass gain that corresponds to the direction of ammonia flow. The only exception was at 750 degrees and dry conditions. But in that case, we had quite a lot of cracking in the reactor. If I remember correctly, we went from 6% at the inlet to slightly below 1% at the outlet. So in that case, we saw some variation, that the sample that was placed on the top was slightly more affected by the sample in the bottom. So in the mass gain results, they're all plotted as an average of the 3 samples, with the error bars showing the variation among them. So you see, for a lot of them, the variation is quite small, actually. For the first question, I'm not sure if I completely understood, but was it whether the increase from 2 volume percent steam to higher steam percentage would have similar effect? Sorry, could you repeat? Or if
yes,
the go ahead.
Maybe Peter want to open the microphone.
Hello. Hi, I'm Peter. Sorry. Yeah, this is my question. That if you're thinking about an SFC system, and if you would like to go higher recirculation rate, water can appear in the gas. So that's would be the main point of my question. That how it's effective if we go much higher with volume percent of water, steam.
Yeah. I think it's a good question. Of course, increasing the steam content will increase your partial pressure of oxygen. So for the alloys that have a tendency to oxidate, they will maybe oxidate more, or you would have a more greater competition between oxidation and nitridation. But the short answer is I don't know. We are hoping to find out. At the moment, we are limited to room temperature saturated steam in our test rig, but we are planning to upgrade it so that we can also run higher steam contents. So it's something that we're planning to investigate in the future.
Yeah, thank you for your answer and the presentation.
Thank you. Okay, maybe we have the very last question. Meanwhile, I recall you that in the chat you can find an info pack, which is a short document that summarizes Velma presentation. So it's the Zenodo link. The very last question, then we move to the next presentation, is how much alumina was added in the EF 100-01 alloy?
Yes, I have the full compositions here. So the EF 101 is sort of a trial composition from Cantel. It contains 3.7 alumina.
We'll give the floor to Antonio Alfano. Wait, you should now be able to present.
Yes, going for that.
Yes, we can.
Hopefully you can see the slides and we are ready to start. I see that the clock is ticking, so I will try to stay on time or save some minutes if possible, but I will be happy to take questions afterwards. So I'm Antonio Alfano, working as a R&D manager for the stack development section here at Elcogen, and today's topic of my presentation is really looking forward in a kind of more a holistic view of what it takes really to operate solid oxide fuel cell stacks with ammonia, starting really from material development and then showing also where we are from operation at stack module level. But first, I would like to start briefly by describing or giving a brief overview about Elcogen, even though most of you might know us, what we are, where we are. We are a company which has been now for more than 20 years in the business, was founded originally in Estonia, and then branched out also in Finland. We are growing constantly. We are around now more than 150 people and keep on growing on that. We are very proud to be welcoming for more than 20 different nationalities across all functions. We are fostering and really encouraging the diversity. We really believe that this is also one of the added value of Elcogen as a company. And we have really a global footprint. We have more than 160 customers spread across the whole world, more than 30 countries covered. And we really believe also that what it takes to drive innovation, which is one of the key elements where solid oxide technology is where we need to drive innovation forward. And to do that, we really rely on the talents, we rely on people. We have more than 50% of the people that are working with us a PhD, and we really value the contribution of everyone in driving this technology forward. We have, since 2022, raised more than 170 million euros, and these are helping us developing forward our technology and also our infrastructure so that we can meet the demand of the market when it's needed, when it comes from everywhere. And the proof that we are on track with that is basically very recent news. Since September 2025, we launched and had the ground opening of the first factory that was opened in Estonia, 14,000 square meters of factory. And this is really the blueprint that we want to use to showcase that this technology can be delivered at scale. We're scaling up from 10 megawatts to 360 megawatt of annual production within this roof. And here we really bring together everything starting from cell manufacturing, ending up to stack production. And the concept behind this factory is really meant to be deployable in different locations worldwide so that we can deliver close to the customers the product which is needed. And this all that we are doing would not be possible without both our key investors and key partners that believe in, trust us in our technology and in our development activities. We have investors such as HD Hyundai, Baker Hughes, SmartCap, and Hydrogen One Capital Ventures, which are backing us up in scaling up our production and developing our technology further so that we can really make sure that we have also the visibility and we have a solid foundation where we develop our technology further. And then we also look beyond our walls, and we really need also all the partners with whom we collaborate and who are using our technology and our products to develop their own products, which then serve the markets for level of system, different stacks. So we have a long-standing relationship with Convion, ADL, Genvia, But Anywhere, Casale, and Buno Fuel Cells. So all these players out there in the market are really supporting us and are working closely together with us to really reach out globally with as wide footprint as possible. I've mentioned already a few times, but what we are essentially developing here at Elcogen really starts from the core of this technology. So we have our proprietary manufacturing of the unit cells, the electrochemical unit cell, which has been now developed for more than 20 years and is already a very robust product which has been tested in many different environments. And then what we also develop is the stack, which is then one step forward in terms of integration. It makes it easier for the customer to really develop the system around it. It allows still the flexibility to design the power rating of that system. The next step forward, which is also something we have been engaged lately, is the modules. So really the building blocks which can be then duplicated within system to meet the power needs. So we are flexible. We provide what the customer needed to fit to develop their own proprietary applications. And those really fit a broad range of technologies, whether it's green hydrogen production, stationary power generation, or more in general Power-to-X applications. In all these products, there is a lot of development, like we mentioned, and this would not be possible without the backing up of the European or publicly funded projects. This picture is basically showing just a high-level view of all the project, most of the project where we are currently involved. You can see also FUELSOME, which is basically the main project where we are here talking about, and all the partners within this project we are working together to enable to meet the project target. So we strongly believe that to drive this technology forward, we need collaboration, and we need really the cooperation with as many players as possible, from research entities to large enterprises. But now let's go a bit more into really the topic here about this webinar, and specifically here what I would talk more about is how do our stacks behave with ammonia, how do they work there, and these are again specifically supported within this FUELSOME project. Really briefly, although it has been already mentioned a couple of times, what happens when you start feeding ammonia to a solid oxide fuel cell. There are several publications on the topic. In this case, you could see basically a simple schematic about what happens when ammonia reaches a unit layer in a stack. In this case, ammonia is then cracked into nitrogen and hydrogen. Hydrogen is then electrochemically converted into fuel, and then you have an exhaust gas which contains a given amount of species depending on the conversion ratio of the at which the cell is operated. The risk, which has been already kind of discussed more than once during this webinar, is what happens if the ammonia is actually not cracked and it does actually react with the steel components. The unit cell itself contains nickel, and that is one of the elements which is prone to react with ammonia to cause nitration. And this effect we have seen has a dependency on temperature and a dependency also on the kind of ratio of species between, for example, ammonia and hydrogen. In the case of a solid oxide fuel cells, the cracking of the ammonia can happen in the support layer of the unit cell, and the rate at which this reaction happens is again dependent on temperature. So the balance between the cracking of the ammonia in the support layer and the reactivity of the unit cell, but then also the other components to the nitridation, eventually determines the operation window of a given stack or a given cell for a given temperature to ammonia. Generally speaking, at around 750 degrees C, the cracking process of ammonia is sufficiently fast to enable to have sufficient hydrogen to prevent the nitridation process. And this is really one of the key also, that the support layer really needs to have this activity toward ammonia decomposition to make sure that the materials do not induce, are not subjected to accelerated degradation. But again, like we have also seen thoroughly during this previous presentation, is that it's not only the unit cell, but all the other BOP components and the stack components themselves need to be assessed and studied against how their tolerance against ammonia is. And what we're really doing in this is what we're addressing here within the FUELSOME project. This has been already presented by Santeri at the beginning of the presentation, so I will not discuss about that further, but I will just focus here basically on what we are doing. So we're really, what we will be discussing here is what we will be doing and studying at research level, but also demonstration level for stack module component, and then eventually going to the kind of laboratory testing. How we're doing this, we have quite of a multi-layer approach, which in a sense also increases in risk when we go from the top of this chart to the bottom. We have seen extensively already what it takes or what it's necessary to do, why it's necessary to do ex situ testing with this kind of coupons, where we really expose materials to different conditions to really down select candidates among a pool of different options. Then we have different platforms: short stacks, full stack, and stack module. Short stacks is something that we use to really study in the first level how do the platform behave for a given condition. And this is a first iteration where we really try to stress test the components and see how they behave. Based on the outputs from those tests, we then typically scale up and go to full stack or modules. And this is where we learn more in terms of components reliability, because here we have 15 layers, here we have 119 active layers. So you also start to see the reliability, and we can study more in a more representative way how those components behave in a kind of more representative environment. And then eventually we go to module testing. We will show a bit of everything in this slide. We have seen already quite a few examples about how coupons of different metals react to ammonia. And what we have also done within this FUELSOME project together with VTT is really studying how those materials react for different temperatures, different operating conditions. Different steels were tested. We also tested protective coatings, 3 of them in different variants of thickness and exposed to different temperatures. And I believe you see something familiar that you have seen in previous slides. You do still have candidates which essentially are destroyed at the end of the test. Others which are looking pretty good, but then it shows also that this is already a good screening to down select some of the candidates which are suitable for operation with ammonia. The next step that we use from there is restarting short stack testing. So 15 layer stack, and then we started feeding increasing amount of ammonia. One of the peculiarities of our stack platform is that the proprietary cell technology enables to work at a very low temperature. The stack is effective at already 600 degrees C. So we're feeding ammonia at a relatively low temperature compared to many other solid oxide fuel cell stacks. What we have done here, we have kept the stack under current. So this is the voltage, average cell voltage kept over time, and we have gradually increased the amount of ammonia that was fed to the stack by keeping fuel utilization constant through mass flow controllers, adjusting the hydrogen flow rate. And what in between every steps, you see this blank space. This is where we were doing basically reference measurement at open circuit voltage to check the gas tightness of all the layers. You can probably see that for up to 2.5 volt percent volumetric percentage of ammonia, the voltage was not substantially changing. We see still a decrease. That's because we see that the endothermic reaction of cracking ammonia is decreasing the voltage because of the temperature decrease. So this is coherent with the results. But then when you go to very high ammonia content, you start to see that the voltage stability is is starting to look more or less stable in that sense. Nevertheless, we also saw that going back to the clean composition, so no ammonia, the voltage was recovered and it was stable. So from these initial experiments, we were able to determine the operation window of the stack and also the possible risk of accelerated degradation. Yet still, we could see that even for more than 5% of ammonia, the the stack lifetime was not impaired. It's still tolerable and it can be recovered. And this is kind of a good feedback in terms of development and kind of setting the parameters for the pre-cracker units. From here, we have then went one step forward. So taking the information from here, we went to this 6 kilowatt module, where we used around 3% of ammonia in the fuel inlet composition. The rest was kind of cracked with the pre-cracker unit. And then we started doing some performance mapping. And what we were able to achieve was to meet the project KPIs in terms of electrical efficiency. At stack level, we have achieved at the rated power, which was 6 kilowatt, close to 60% of electrical efficiency. So this is, again, a good indication because we have seen thoroughly that the material challenges are applicable to all levels of integration. It's not only the stack. And to make sure that you would crack completely the ammonia before reaching the stack, you would need to really sacrifice and oversize also the pre-cracking units. But if you have a stack which is actually tolerant to some of the ammonia, you could still optimize your system design to maximize the overall efficiency. But in conclusion, what I would like to emphasize is that really making next generation energy system based on ammonia and solid oxide fuel cells is possible and can be achieved, but it really requires a kind of a synergistic effort, which really goes from stack to BOP components to really bring all the things together and optimize them, taking into account the material challenges which apply to all the components which are eventually in the system. Ecogen stacks have been demonstrated to be able to operate with ammonia, with a fuel composition which contains some uncracked ammonia, even at relatively low temperature, close to 600 and 650 Celsius degree, achieving close to 60% electrical efficiency. Again, a good show, also showcase for the stack platforms, which is one, but is able to fit many different applications. Again, possibility to operate with different fuels, different operation modes, so that the same product can really fit a broad range of commercial applications. And this would be my final slide. And I don't know if we have time, but I could take some questions.
Thank you. I would say just one or two questions, and then we have to move as we are running late. Maybe at the end we can recover the
Yes, exactly. One question for you is from Arash. The efficiency presented is with the anode of gas recirculation. How much is the fuel utilization in stack? Thank you.
So in that, since this was a laboratory test bench, it was not possible to equip the unit with an anode of gas recirculation. So it was a single pass efficiency, and the single pass fuel utilization. The fuel utilization at stack level was in the order of 75%.
Okay, thank you. One more question.
Can you describe briefly the recovery process from 5% NH3 operation point?
Basically, what we have seen is that even though the voltage degradation is increased when you are exposing the stack to more than 5% ammonia, if and when the ammonia concentration is decreased, the voltage does not keep decreasing with the same degradation rate as it was seen for the higher ammonia concentration. So the stack can tolerate for short-term higher amount of ammonia, and when the operation is brought back to the safe operation window, the stack lifetime is still preserved.
Okay, just the very last question, then we have to move on. You show decrease of OCV with NH3 concentration. How do you separate between irreversible degradation and the lower OCV expected from a direct NH3 fueling versus H2?
The open circuit voltage was measured always with the same composition, which did not contain ammonia. We always went back to a clean hydrogen-nitrogen composition. The voltage that was shown was undercurrent, and that was indeed because of the different gas composition. So the OCV was always assessed with the same composition back without ammonia content.
Okay. Thank you so much. So our next presentation will be by Debasis Chakraborty. I'm sorry if I mispronounced the name, and I give you the permission to share. Okay, now we can see. Thank you.
Okay, yeah. And you can hear me, right?
Yes, we can hear you.
Hello, everyone. Sorry for the glitch to start with, but that's how it is. My name is Debashish Chakraborty. I work at the Electrolyzer and Fuel Cell Technologies business unit at Alfa Laval. And today I'm going to talk about protecting stainless steel when ammonia is used with SOFC. This is, in my view, this is still like an ongoing field and development, and there are so many surprises that we sort of faced when we started doing that. So it's good to be part of this webinar. First, it's Alfa Laval at a glance. So we were founded 140 years back. We are over 20,000 employees. There are 3 key technologies: heat transfer, separation, fluid handling. And we are an innovative company. We pay a lot of importance to patents and innovation. Then comes AMON project, where we are using a novel system for utilizing ammonia for a high efficiency energy generation with SOFC. It will be like a 8 kilowatt demo system that will be demonstrated at site, one of our partner sites. Just one thing I would like you to notice that there is a cracker here, even though it's an SOFC. And this is the consortium, FBK as the coordinator. We have Solidera, us, Alfa Laval, Sol, QA, VTT, DTU, EPFL, European Fuel Cell Forum, and HSLU, Lausanne. Okay, I just, this has been described. So, you know, ammonia is like the perfect fuel for SOFC. A lot of hydrogen, easy to store ammonia, and then there is no carbon dioxide emission. However, there are a lot of challenges that we have been figuring out, and that's like the material degradation. I mean, nothing. When we are talking about stainless steel, I'm not talking about exotic material, which are very expensive, but stainless steel, nothing could tolerate ammonia at this elevated temperature. This is, you see, 310S exposed to pure ammonia at 6.5 hours at 600 degrees centigrade, and see what happens to this. This is like terrible, right? Before and after. And then if you see what is in there after exposing to ammonia, this is 100% ammonia, just so that you remember. You see a lot of nitride. There is also oxide. That was a surprise to us, but there's a lot of nitride that is formed. And if you see close up, you see this kind of big crystals on the surface, and then these are actually oxides. These are chromium oxides, but you also see a huge amount of nitrogen on the surface. So the surface layer, that is the protective layer, the chromium oxide layer, that is totally disintegrated when exposed to ammonia at these temperatures. If you see what happens when the exposure time increase, you see more nitride forming. So amount of nitrogen increases, and this is just 24 hours. And we're talking about 20,000 hours or 10,000 hours of durability of this kind of things, right? So it's really challenging. And then this is 316L. This after treatment looks not as bad as 310 visually, but you see a lot of nitrogen still. So nitride is forming, the chromium layer is gone, chromium oxide layer is gone. And what are the reasons? The main reason is the availability of atomic nitrogen, because somehow this chromium oxide, a little bit of it, or some little bit exposed metal dissociates ammonia, and you have atomic nitrogen and hydrogen, and then this also kind of reduces the protective chromium oxide layer. And as you can see, all the elements like chromium that protect stainless steel against corrosion, like chromium, iron, nickel, they all like have quite a high affinity towards nitride formation. So the entire structure disintegrates, and this is something that we cannot really avoid. When the temperature is elevated and you have ammonia, there will be corrosion, and significant corrosion. Okay, then what are the strategies? I mean, there is no way to avoid corrosion, so you need to come up with some strategy. So this is something that we try to follow, like, okay, a thermal barrier coating. So this thermal barrier coating could be a ceramic, like HUS stabilized zirconia, and this could lower the temperature, because lower the temperature, the less dissociation of ammonia, and in that way reduce the nitrogen atom concentration on the surface. A protective layer that could be alpha alumina, because alpha alumina is pretty much non-penetrable to nitrogen. As you can see at 700, the diffusivity is order of 10 to the power -6 compared to 10 to the power -12 for Okay, this is reversed actually. 10 to the minus 6 for alumina compared to 10 to the minus 12 for chromia. So, and then there is a metallic protective layer that could be applied, and that layer could be like a nickel rich layer. And as we have already seen before, nickel reduces the solubility of nitrogen in the metal. And when you do that, it could look something like this. So this could be a good protective layer, and basically depending on your application, you have to choose. And then there are challenges like adhesion and compatibility. So compatibility with other layers and base material in terms of, for example, thermal expansion coefficients, because they could have different thermal expansion coefficients and things will fall apart. Then this is very important that the protective layer needs to cover entirely. You know, if you have just a hairline crack, and that will be the point of attack. So that is very important, and that's why multi-layer coating is probably a way to go. And then possible detrimental changes in the base metal by substituting, you know, the elements of the base metal with the coating material. And then polishing after treatment. This could also pose a lot of challenges. There are different methods available to do that. Chemical vapor deposition, physical vapor deposition, thermal spray, slurry method, and one could choose based on what kind of thickness and what kind of geometry one is looking for. But there are methods available. And then there is this slurry method where one could make this aluminides. And this is basically putting aluminium layer on top of the stainless steel. And this layer could be thick, thin, depending on how you want it. But here it's like 75 to 80 nanometer, micrometer thick. And as you could see, as you go down, the concentration of aluminium goes down. And this could be a good way to protect the stainless steel. And that's because when this is exposed to air, you form this alumina layer. And then there is, I mentioned that even though we were doing SOFC-based power generation with ammonia, in Ammon project, we have a cracker. And that's because a cracker could act actually as a first line of defense for reducing ammonia concentration significantly. And by doing that, it could save the rest of the BOP, including the SOFC. And as you can see here, when the cracking temperature or the temperature in the cracker is around 600, you have very little ammonia left, around 500 ppm, right? So if you could feed the cracker with that kind of heat and then flow ammonia through, then you have very little ammonia left in the stream. And as you can see here, this is from this paper by Arosh. And then you can see the temperature, basically the nitridation potential decreases as the degree of cracking goes up, right? So in practice, if you are above 90% cracked ammonia, you should be kind of okay. to operate the stack as well as the rest of the balance of plant. So this is what we are doing. We are using our heat exchanger and coating the plates and converting it to a cracker. So one channel is coated with cracking catalyst, and the next channel is for hot gas to provide the heat for cracking. And this is a very nice system because this is like scalable up and down depending on the number of plates we could add, and also it has low pressure drop. So the conclusion is at elevated temperature, ammonia corrodes stainless steel. It's inevitable. And then the normal chromium oxide protective layer of stainless steel is not effective because of nitridation. Coating, especially multi-layer coating, can prevent ammonia corrosion. So you should think about that. For SOFC-based power generation, this is not applicable everywhere, but for SOFC-based power generation, when ammonia is used as fuel, cracker can act as the first line of defense. And there is a nice compatibility of the outlet exhaust temperature of the SOFC and cracking temperature. So that's basically what I have, but then I need to show you this a few more webinars like this that are coming and organized or co-organized by AMON. So here are the webinars. So feel free to join, and there will be publicized. So basically, you will know about this, and they are related to ammonia and power generation for maritime sectors, mainly focusing on. Okay, thank you. And then if there is time, I'll be happy to take a few questions.
Thank you. I take the chance to suggest all the participants to follow our project, so Single, Amon, and FUELSOME on social media to be updated on next webinar and other activity. Is there any question? We can take few minutes if you have question for the Basish or the other speakers. Belma maybe want to intervene.
No, I was wondering if I could ask a question if you don't have any in the chat waiting.
Yes, yes.
For the Bashi. Yes, so I'm curious to see the cracker that you are planning to use. I saw was planned in 310S or 310L.
No, yeah.
Alloy, no.
So the material that we are using at present is 316L.
Do you believe that you can operate that as a cracker without any nitridation issues, or are you planning to coat it to?
No, we plan to coat it. Yes, okay. I mean without coating it, like I showed, right? It will not survive beyond 10, 20 hours probably. I mean, it has that's just the material properties, right? So, and we do not want to use exotic materials. That's so we want to use 316L or 310, but then apply coating.
Thanks.
Yeah.
Thank you. Any other question? now. If not, I will say thank you to all the speakers, of course, but also to the attendees. It has been very interactive. Thank you for the questions, for all the speakers, and again, follow our projects on social media and on the website to stay updated, and for other webinar related to ammonia as a fuel. Thank you again, and enjoy your day.